Hello, everyone, and welcome back to the Theory and Algorithms of Knowledge Tracing series. Today, we're taking a significant step forward. We'll explore a model that addresses one of the biggest limitations of the classic BKT, its short memory. This model is called Dynamic Bayesian Networks, or DBN for short. By the end of this video, you'll understand exactly how DBN works, how it's a powerful upgrade to BKT, and how to calculate it with a real example. Let's get started. To understand DBN, let's start with a simple analogy. Think of BKT, the model we learned before, as a teacher with a very short memory. Every day, this teacher only looks at the student's performance from the previous day to make a judgment. Now, think of DBN as a detective. This detective doesn't just look at yesterday's clues. They have a complete timeline of the case, and they understand the complex web of relationships between different pieces of evidence. DBN is this detective. It's a more powerful, generalized version of BKT that can remember the past and model complex interactions. All right, let's break down the key concepts that make up a DBN. First, we have nodes. These are just the variables we care about. Next, we have time slices. Imagine slicing time into individual moments. Then we have transitions, the probability that the state changes. Emissions are the probabilities that link the hidden state to the observable outcome. To make this all manageable, we use conditional independence. Finally, unrolling is the visual process of drawing the network across time. The magic of DBN lies in its core formula, which breaks down the complex joint probability into a product of simpler conditional probabilities. Now, here's where DBN truly shines and upgrades BKT. In BKT, xt only depends on xtt1, but in DBN, we can have higher order dependencies, meaning xt can depend on xtt2 or even further back. We can model multivariable coupling, where mastering one skill helps with another. And we can add contextual nodes like fatigue or motivation. This is the mathematical engine that gives DBN its long memory and modeling power. Enough theory. Let's get our hands dirty with a concrete example. We're going to track Xiaoming's progress on learning linear equations over 3 attempts. We'll use a second-order DBN, which means it can remember the state from the 2 previous attempts. First, let's define our parameters. This is our transition probability table, or CPT. It tells us the probability of mastering the skill at time t, given the mastery states at t92 and t91. This is the key to modeling long-term memory. Let's start with the first attempt. Xiaoming gets the question right. Since this is the first attempt, we don't have any prior history, so we fall back to a simple initial probability, just like BKT. We assume a 30% chance he knew it from the start. Using Bayes' rule, we update this belief based on the correct answer. The calculation gives us approximately 0.708. So, after the first correct answer, we're about 70.8% confident that Xiaoming has mastered the skill. Now for the second attempt. Xiaoming gets it right again. We now have one prior state, t=1, so we can perform a transition step. We use a standard transition probability of 0.8, meaning if he knew it before, there's an 80% chance he still knows it now. This gives us a new prior belief of about 62.5%. We then update this belief with the second correct answer using Bayes' rule. The result is approximately 0.904. Our confidence in Xiaoming's mastery has jumped to 90.4%. Here comes the exciting part, the moment where DBN truly shows its power. It's the third attempt, and Xiaoming gets it right again. Now we have 2 prior states in our history, t=1 and t=2. Our second-order DBN kicks into gear. We look at the combination of the previous 2 states, which were both high. We check our CPT table, and it tells us the transition probability for high is 0.90. This is higher than the standard 0.80 because the model recognizes a solid, consistent foundation. After updating with the third correct answer, our final mastery probability is approximately 0.963, or 96.3%. So, what's the difference? Let's compare our DBN result with what a standard BKT model would have calculated. BKT only looks at the immediately preceding state, t equals 2, which was high. It would use the standard transition probability of 0.80, leading to a final mastery probability of about 93.1%. Our DBN model, however, looked at the history of t equals 1 and t equals 2 and recognized a pattern of consistent high performance. It used a higher transition probability of 0.90, resulting in a final probability of 96.3%. This difference shows that DBN is more confident in the student's mastery because it understands the stability that comes from a solid learning history. So, how do we get all these probabilities, like the numbers in our CPT table? DBN learns or is given several types of parameters. We have the initial distribution, which is our starting belief. The transition CPT defines how the state changes, and the emission CPT defines how the state leads to an observation. Beyond the numbers, we also have structural parameters, the structure of the network, and the time span, or order. Traditionally, these parameters are learned using algorithms like expectation maximization, EM. But in the modern era, we often replace these fixed tables with flexible neural networks. Let's summarize why DBN is such an important model in knowledge tracing. Compared to BKT, DBN has a much longer memory span, can model multiple skills and contextual factors simultaneously, and can even capture how different skills interact with each other. And importantly, it maintains high interpretability through its CPT tables. This isn't just theoretical. A recent 2026 survey paper highlighted that temporal models like DBN are essential because they can capture temporal dependencies. This means they account for the fact that learning isn't just about the last thing you did. The foundation you built days or weeks ago matters. So, to wrap up, DBN is a powerful generalization of BKT. Its superpowers are its ability to model long-term memory and complex interactions between different skills and factors. Despite this increased power, it remains highly interpretable. Think of DBN as the crucial stepping stone that bridges the gap between simple, interpretable models like BKT and the deep learning models we'll explore in future videos. It's the key to understanding not just what happened last, but the entire journey that led to the student's current state. That's all for today's deep dive into dynamic Bayesian networks. I hope this step-by-step explanation has made this powerful model clear and accessible. If you have any questions, please leave them in the comments below. Don't forget to like and subscribe for more content on the theory and algorithms of knowledge tracing. Thanks for watching, and I'll see you in the next video.